We're going to do an example now where we use a vector loop equation to solve this 3D geometry problem. Here's the description of the problem. It says a laser beam, which comes from body A, hits point Q of this vertical cylinder, which we're calling B, and the cylinder has radius 1. Next, the point of B's symmetry axis, which is in contact with N, is denoted BO, and its position from NO is given as 5nx plus 2nz. Next, we're given that the direction vector of the laser beam is 3nx minus ny plus nz, and we're going to just refer to that as some vector d. Finally, we're given that the position vector of AO from NO is nx plus 2ny. So finally, the question here is to find the distance between point AO and point Q. So in other words, what we need to find is the magnitude of the position vector of Q from AO. Before we get going, I'm going to point out that this is not a planar problem. We can't use some sort of trigonometry like this to determine the length between AO and Q. Because if we draw a triangle like this, we're assuming that everything is in the plane. But in fact, this direction vector tells us that there is a component that comes out of the page. So this simply won't work. Instead, whenever we're asked to find some kind of distance, we can use vector geometry, and specifically, we can write a vector loop equation to solve for any unknowns that we need. We've already defined the position of AO from NO and the position of BO from NO. So let's go ahead and label the position vector of Q from AO and the position vector of Q from BO. To define the position vector of Q from AO, we can observe that it has the same direction as D, which I'll go ahead and draw in like this, but it has a different magnitude. So in short, I'm saying that the position vector of Q from AO is some scalar multiple of this direction vector. So one of the unknowns we'll want to solve for is the value of lambda, and I go ahead and rewrite this as lambda times this direction vector. Now we'll recall that Q is actually an unknown point, so the position vector of Q from BO contains other unknowns. For now, we just write the position vector in terms of some unknown quantities, x, y, and z, meaning that to get to Q from BO, we're going to go some amount x in the nx direction. Of course, it looks like x will be negative. We're going to go some amount y in the ny direction, and we're going to go some amount z in the nz direction, which could be in or out of the page. Now, a clever thing that we're going to need later is to realize that there's a relationship between x, y, and z here. These aren't completely free variables. Because Q lies on the surface of the cylinder, y is relatively free, but x and z are actually constrained to satisfy the equation of a circle. So essentially we have that x squared plus z squared must be equal to the radius squared, and of course the radius is 1. So if we rearrange this, we get 0 equals x squared plus z squared minus 1. So here we have one scalar equation. And if we look back, we have 4 unknowns, lambda, x, y, and z. So we're going to need 3 more scalar equations in order to solve our problem. And we'll be able to get those 3 scalar equations by writing an equation that takes us in a loop with 0 displacement. So hence we have a 0 displacement equals the sum of these position vectors. So say we start at NO, we're going to go plus the position vector of AO from NO, and then we're going to go plus the position vector of Q from AO, and then we're going to go in the opposite direction of the position of Q from BO. So we'll just apply a minus sign. And then again, we're going to go opposite the position vector of BO from NO, so another minus sign. So in this equation, we've plugged in the values of all the position vectors. And we could simplify this, but really we'll just continue from here. The key idea is that this 3D vector equation contains components from at least 3 linearly independent unit vectors, in this case nx, ny, and nz. This means that we can dot both sides of this equation by 3 linearly independent unit vectors and get 3 linearly independent scalar equations. And if we think back, we said we needed 4 equations to be able to solve for all our unknowns, and we already have 1 here. So when we add 3 from here, we'll be good. So first we'll dot both sides of this equation with nx. On the left we have nx dot 0, which is 0. And on the right, the result is going to be that we'll keep each nx component because nx dot nx is 1. But the ny and nz components will go to 0. So the result is 3 lambda, which comes from here, minus x, and then minus 5 plus 1, which is minus 4. So here we have one scalar equation. When we dot with ny, again, on the left we'll have 0, and on the right we're basically going to keep the ny components. So here we have 2, which comes from here, a minus lambda, and a minus y. Finally, we dot with nz, which gives us a plus lambda from here, a minus z from here, and a minus 2 from here. So here, by dotting this vector equation with 3 linearly independent unit vectors, we get 3 scalar equations. So the next step in solving this problem is to solve this system of 4 nonlinear equations. These 3 are linear, but this one is nonlinear. And we're going to solve that for values of x, y, z, and lambda, which satisfy all 4 equations. Notice that because of this equation, there's going to actually be 2 solutions. We can interpret that geometrically as one point where the laser first touches the cylinder, and the other point where the laser passes through and touches the cylinder on this side. And what we'll do once we have the value of lambda is simply compute the magnitude of this vector as lambda times the magnitude of d. Of course, if we wanted to know where point Q is, we would also have that information in the form of x, y, and z. But for this problem, we actually don't care. And if you actually carry out this computation, you'll find that the result is 3.83 meters. But I'll leave the actual computation up to you.